Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 49, in which I will discuss the concept of solution of congruences. Now, I will describe the solution of congruences. Let fx is a polynomial of degree n, fx equal to a n x to the power n plus a n minus 1 x to the power n minus 1 plus dot 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 plus a1x plus a naught, where a n minus 1 dot 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 a1 a naught are integers. Therefore, fx is a polynomial of degree n in which coefficient of each term is an integer. Let m is a positive integer and u be an integer such that if u is congruent to 0 modulo m, then u is said to be a solution of the congruence. Then u is said to be a solution of congruence. fx is congruent to 0 modulo m. We know that if u is congruent to v modulo m, then function of u is congruent to function of v modulo m. Therefore, if u is congruent to 0 modulo m, implies that if v is congruent to 0 modulo m. Therefore, v is a solution of congruence. fx is congruent to 0 modulo m. Therefore, v is a solution of fx congruent 0 modulo m. Hence, we get that if u is a solution of congruence, fx is congruent to 0 modulo m, and any integer which is congruent to u modulo m, then that integer is the solution of the congruence fx congruent to 0 modulo m. Now we shall define the number of solutions of congruence fx is congruent to 0 modulo m. Let fx is congruent to 0 modulo m, and r1 r2 rm be complete residue system modulo m, then number of solutions of congruence fx is congruent to 0 modulo m be the number of Ri such that if Ri is congruent to 0 modulo m. Example, let fx equal to x square plus 1. Now, fx is congruent to 0 modulo 7 implies that fx means x square plus 1 is congruent to 0 modulo 7. Now, we have to find all those values of x such that they are member of complete residue system modulo 7 and satisfies this congruence fx is congruent to 0 modulo 7. That means we have to find the positive integers less than equal to 7 and satisfies this congruence. We may not get such positive integer which satisfy this congruence. If we take x equal to 1, then here 1 square plus 1 means 2. 2 minus 0 means 2 is not divisible by 7. Similarly, if we take x equal to 2, then we get result 5 which is not divisible by 7. And we may not get any such integer. So, here we get no solution. If we take m equal to 5, then fx is congruent to 0 modulo 5. Implies that x square plus 1 is congruent to 0 modulo 5. If we take value of x 2 square means 4 plus 1 5 is divisible by 5. That means gives remainder 0. Therefore, one solution is 2. Again, if we take x equal to 3, 3 square means 9 plus 1 equal to 10, which is divisible by 5. That means gives remainder 0 when 10 is divided by 5. That means 3 is another solution of this congruence, and we get two solutions 2 and 3 of this congruence. Now we take another example. Let gx equal to x square minus 1 and congruence gx is congruent to 0 modulo 8. Implies that x square minus 1 is congruent to 0 modulo 8. Now we have to find the solution of this congruence. Now if x equal to 1, we get 1 square minus 1, 0. 0 minus 0 is divisible by 8. Therefore, 1 is a solution. If we take x equal to 2, 2 square means 4 minus 1 equal to 3. 3 minus 0 means 3 is not divisible by 8. So, 2 is not a solution of this congruence. Now, we put x equal to 3. 3 square, 9 minus 1, 8 is divisible by 8. That means this gives remainder 0. Therefore, 3 is another solution. Now, we take 4. 4 square, 16 minus 1, 15 minus 0 means 15 is not divisible by 8. Therefore, 4 is not a solution of this congruence. Now we put x equal to 5. 5 square means 25 minus 1, 24 minus 0, 24 is divisible by 8. That means it gives remainder 0. Therefore, 5 is a solution of this congruence. It is clear that 6 is not a solution of this congruence. Now we examine for x equal to 7. 7 square means 49 minus 1. 48 minus 0, 48 is divisible by 8. That means 7 is another solution. These all are members of complete residue system modulo 8. Therefore, we get 4 number of solutions of this congruence. Now we define root of fx modulo p. P is a prime number. Let p is a prime number, then r is said to be root of the congruence. Fx is congruent to 0 modulo p if fr is congruent to 0 modulo p. If r is congruent to s modulo p, then we know that fs is congruent to 0 modulo p. Therefore, every integer which is congruent to R modulo P is a root of congruence fx is congruent to 0 modulo P. When R is a root of congruence fx is congruent to 0 modulo P, then we say that fx is congruent to 0 modulo P has a solution x is congruent to R modulo P. Now we give examples. Example. Let fx equal to x square plus 2x minus 3 and p equal to 3. Now fx is congruent to 0 modulo 3 implies that x square plus 2x minus 3 is congruent to 0 modulo 3. If we put x equal to 1, we get 1 square plus 2 multiply 1 minus 3, that is 1 plus 2, 3 minus 3 equal to 0, and 0 minus 0 equal to 0, which is divisible by 3. Therefore, 1 is a root of fx is congruent to 0 modulo 3. Now we take x equal to 4. Therefore, x square plus 2x minus 3 equal to 4 square plus 2 into 4 minus 3, that is 16 plus 8 minus 3, 24 minus 3, 21, which is divisible by 3. Therefore, 4 is a root of fx is congruent to 0 modulo 3. Now we take another example. Let gx equal to x square plus 3 and p equal to 5. Now gx is congruent to 0 modulo 5 implies that x square plus 3 is congruent to 0 modulo 5. If we put the value of x equal to 1, then 1 square plus 3 equal to 4 minus 0 equal to 4, which is not divisible by 5. If x equal to 2, 2 square means 4 plus 3, 7 minus 0 equal to 7, which is not divisible by 5. If we put x equal to 3, 3 square means 9 plus 3, 12 minus 0 equal to 12, which is not divisible by 5. If we put x equal to 4, 4 square means 16 plus 3, 19 minus 0 equal to 19, which is not divisible by 5. In this way, we may not get any value of x, means any integral value of x, such that this congruence is satisfied. Therefore, we may not get any root of this congruence. Now we define degree of the congruence. Fx is congruent to 0 modulo m. Let fx be a polynomial of degree n. Fx equal to an x to the power n plus an minus 1 x to the power n minus 1 plus dot 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 plus a1x plus a naught, where coefficients of each term an minus 1 dot 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 a naught, all are integers. Let m is a positive integer and an is not congruent to 0 modulo m, then degree of congruence fx is congruent to 0 modulo m is n. And if an is congruent to 0 modulo m, but j be the largest number such that aj is not congruent to 0 modulo m, then j be the degree of the congruence. Fx is congruent to 0 modulo m. If there is no such integer j such that aj is not congruent to 0 modulo m, that is, if all the coefficients are divisible by m, then no degree is assigned to the congruence fx is congruent to 0 modulo m. Now we write this. If there is no such integer j, that is, if all coefficients of terms of polynomials are multiples of m, then no degree is assigned to the congruence. It should be noted that degree of the polynomial and degree of the congruence are not always same. Degree of congruence depends on modulo. By an example, we may verify this. Example. Let gx equal to 6x cube plus 3x square plus 1 is a polynomial. Here degree of polynomial equal to 3. Since highest power of variable x is 3, let m equal to 5. Here 5 does not divide 6. Therefore 6 is not congruent to 0 modulo 5. Therefore, degree of congruence gx is congruent to 0 modulo 5 is 3. Therefore, in this case, degree of polynomial and degree of congruence be same, that is 3. If m equal to 2, then 2 divides 6. That means 6 is congruent to 0 modulo 2. But this coefficient 3. But 2 does not divide 3 implies that 3 is not congruent to 0 modulo 2. Therefore, degree of congruence is 2. Here power of x is 2. Therefore, degree of congruence gx is congruent to 0 modulo 2 is 2. Since degree of the polynomial is 3 and degree of this congruence is 2, therefore degree of polynomial is not equal to degree of congruence in this case. Now we shall prove a theorem. Theorem is if d divides m and d greater than 0 and if u is a solution of fx is congruent to 0 modulo m, then u is a solution of fx is congruent to 0 modulo d. Now we prove this. Given that d greater than 0 and d divides m implies that m equal to dk1. k1 is an integer. This is number 1. Also given that u is a solution of congruence fx is congruent to 0 modulo m. Let this is number 2. Implies that if u is congruent to 0 modulo m. This is number 3. We know that if A is congruent to B modulo M, implies that M divides A minus B, implies that A minus B equal to M K2. K2 is another integer. This is number 4. Implies that A minus B equal to, here we use number 1, M equal to dk1, dk1, here k2, using 1. Implies that A minus B equal to D, let K1 multiply by K2 is K. Let K1 multiply K2 equal to K is an integer. Implies that D divides A minus B. Implies that A is congruent to B modulo D. This is number 5. Therefore, we get if A is congruent to B modulo M and D divides M, implies that A is congruent to B modulo D. This is number 6. Since from 3, if U is congruent to 0 modulo M and D divides M, implies that if U is congruent to 0 modulo D. Therefore, U is a solution of congruence. Fx is congruent to 0 modulo D. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.